Most of the beginners think that while using the ADC of ESP32, we would get the values in the range 0 to 4095 for one complete rotation of this potentiometer, as you can see over your screens. And this is correct, there is no problem in that. But this time you will see that the value 4095 will be achieved somewhere here at this point. And if I rotate the knob further, you can see the value is not increasing. So I will explain that why this is happening. Now you can also change the resolution of the ADC of ESP32, not the core hardware but using the program. Like this time I will rotate the knob of this potentiometer and you will see the maximum ADC value will be 1023 and not 4095. Now before moving further we need to understand ADC. So ADC converts a voltage which is nothing but an analog signal into a number, and ESP32 ADC is different from that of Arduino. So the ADC in ESP is of 12 bits and its resolution is 1.1 volt, which is the hardware limitation of this ESP. But if we talk about the Arduino, its ADC is of 10 bits and the resolution is 5 volt. Now, in case of ESP, suppose if we provide voltage greater than 1.1 volt to the ADC, not to the ESP but to the ADC. ESP32 is powered from 3.3 volt, that is a separate thing. Then the ADC value would saturate very quickly. So the ADC value is calculated internally using this formula. Input voltage multiplied by 4095 divided by 1.1. So input voltage is the potential difference between this ground pin and the ADC pin. Now in my case this potentiometer middle pin is connected to GPIO number 34 on the ESP. And this 4095 is the maximum ADC value the ESP32 ADC can achieve, divided by 1.1. Now this 1.1 is the reference voltage for the ADC. Now suppose if we provide voltage, that means input voltage greater than 1.1 volt, then the ADC value will be greater than 4095. But you see that analog read function always gives the value 4095 and never crosses this value. So what is happening here? And the answer is attenuation. So attenuation means scaling down or reducing the input voltage, which is the difference between this ground pin and pin number 34. So attenuation means to weaken something. So before this input voltage reaches the ADC, we scale it down. And I will also discuss more insights about this attenuation concept further in the video. Now you need to know that the attenuation value are giving something like this: 0 decibel, 1 decibel, 6 decibel, 11 decibel, and 11 decibel is the maximum attenuation value for the case of ESP32 ADC. And inside the ESP32 chip there is a network of resistors, which is nothing but a voltage divider. Okay, and these resistors are etched onto the chip of the ESP32. Now suppose if input voltage is less than or equal to 1.1 volt, then in this case this terminal is connected directly to the ADC and this voltage divider is bypassed. Okay. Now suppose if input voltage is greater than 1.1 volt, then in this case what would happen? The ADC value would be greater than 4095, which is not possible. So in this case this terminal first connect to V in terminal of this voltage divider, and obviously the voltage value at this terminal V out will be less than V in, and then this V out value is further fed into ADC. So this resistor network is designed such that the voltage value at this terminal is always 1.1 volt. So in this table 4 parameters are given, like attenuation value, resistor network status, ADC input limit, and here this voltage is the maximum voltage limit and the corresponding scale factor. So if the attenuation value is 0 decibel, it means resistor network would be bypassed, it means it will be off, and the ADC input limit is 1.1 volt, which is the same as the reference voltage, and that is why the scale factor is 1. Now as we increase the attenuation value above 0 decibel, like 1 decibel, 2 decibel, 2.5 decibel, so the resistor network comes into play. It means it becomes on, and the corresponding ADC input limits are given here, and also the scale factors. So for the attenuation value of 6 decibel, the ADC input limit is 2.2 volt and the scale factor is 0.5. Okay, so VADC is calculated using this formula. So VADC is equal to V in multiplied by the scale factor. So scale factor is coming from this voltage divider formula. So scale factor is equal to R2 divided by R1 plus R2. And this VADC is nothing but this V out here. Okay, and after calculating this VADC, we fed this into this formula. So input voltage will be replaced by this VADC, and here V in is nothing but these values: 1.1, 1.5, 2.2 and 3.3. So as I said, these input voltages are the maximum voltages. So if you input these voltage here in place of V in and multiplied by the scale factor, you will get the VADC, which is the maximum value, because here voltage are also the maximum. So VADC will be coming out to be 4095. Now without attenuation, some of the data of the analog signal is lost. Now without attenuation means 0 decibel. So if you recall from the starting of the video, the values were saturating very quickly around this point, right? And were not increasing further. It means whatever the data we were getting from the analog signal in this range after this point, that is being lost. But after using attenuation value of 11 decibel, we were able to make use of full range of this potentiometer, and the maximum value we are getting at this point, at the extreme end of this potentiometer. Now here is the program for the ADC, and you can see I am using the attenuation value of 0 decibel using this function analog set attenuation. And in the loop function I am connecting the middle pin of the potentiometer to GPI number 34 of the ESP, and voltage is calculated in this line. So ADC is calculated using this formula. VADC is equal to Vin multiplied by the scale factor. So this entire calculation is being done inside the analogRead function. Okay, and this voltage is calculated using this formula. ADC value is equal to input voltage multiplied by 4095 divided by 1.1. And why I am using 1.1 here? Because if you see from this table, for the 0 decibel we get the ADC input limit of 1.1 volt, and I am printing the values of ADC and the voltage up to 2 decimal places. Now in this program I am using the ADC value of 11 decibel, attenuation value of 11 decibel, and the input voltage limit is set to 3.3 volt, right? Because for 11 decibel the maximum input voltage limit is 3.3 volt, and rest all other things are similar to the previous program. Okay, here is 1.1 and here is 3.3. So with this program you will see that we will get the maximum ADC value for the full range of the potentiometer. But for this program the saturation will occur very quickly, because for both the cases we are providing the input voltage to the potentiometer equal to 3.3 volt. Now one important point to note here is that the default value for the attenuation is 11 decibel. So even if you comment this line and upload the program, you will see that we will get the maximum ADC value of 4095 for the one complete rotation of the potentiometer. Now if you remember, I also said in the starting of the video that we can use the ADC resolution of 10 bit instead of 12. So we can do using this function analogRead resolution. So 10 is the resolution of the ADC. Now if you upload this program, and you will see that the maximum ADC value this time we will get 1023 instead of 4095. So if this project helped you some way, then make sure you subscribe to my channel for more such explanation and tutorials. And if you have any doubt regarding this project, comment in the comment section, and I will meet you with the new project in next video.